Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over how to use molarity as a conversion factor in equation stoichiometry. So let's get into this. So as I have written here, in previous videos we talked about doing a mass-to-mass conversion using stoichiometry, where you have units of mass of one substance, and then you're going to use a conversion factor to convert to grams of that substance, and then can use molar mass to convert to moles of that substance. And then once you get the moles, then you could use the mole ratio from your balanced equation in stoichiometry to go to moles of a different substance. And then from there, go wherever the problem is taking you, right? So I could go to moles of the second substance, or grams, or some other unit of mass. So when we're talking about using molarity, here we're talking about going from probably a unit of volume that they're giving us, and going from liters and then getting to moles using the molarity. So remember, in any stoichiometry problem, the goal is to first take whatever they give you and get to moles. Once you get to moles, you can then use your mole ratio in the balanced equation to convert to whatever the other substance is that you're interested in, and then from there convert to whatever unit that you need to get to. So if we start with a unit of volume, maybe we need to get the moles through molarity, and then once we get here, maybe they want the mass of substance 1, or maybe they want the mass of substance 2, or maybe they want the volume of substance 2, right? So maybe you'll need to use molarity again, which in this problem we will. So let's go ahead and look at this problem. So when we're doing a problem involving molarity, use molarity as a conversion factor. So there's might be more than one way to solve this problem. I'm going to show you what the way I really like is using molarity as a conversion factor to just keep converting until you get to the end of the problem. So here we're asked how many milliliters of 6.00 molar HNO3 nitric acid are necessary to neutralize the carbonate in 75 milliliters of a 0.250 molar solution of sodium carbonate. Okay, so the first thing we need in order to do stoichiometry is a balanced equation. So we need to put our reactants together, see what products are formed, and then balance the equation. So we're told that we have HNO3. So I'm going to write HNO3. That's going to be aqueous because it's an acid. I'm going to add to that. I'm going to react that with sodium carbonate because I want to neutralize the carbonate. So that's going to be Na2CO3, and that's going to be aqueous as well. And then these two are going to come together to form the products. So we can treat this as a double displacement or double replacement reaction. So even though this is an acid, it's molecular, it will ionize and become ions. So we could put the H with the CO3, the carbonate ion. So that will form H2CO3. And here, let me get that a little bit further. So that's going to be, what did I say? Say H2CO3. And so the next thing is going to be that the two ions in the inside, sodium is going to go with nitrate. So we get the sodium nitrate. And that's going to be NaNO3, like so. This is going to be aqueous because all nitrates are soluble in water according to the solubility rules. H2CO3, that's carbonic acid. That's also going to be aqueous. Okay. So now that we have all of our reactants and products, now all we need to do is balance the equation. And so we're going to balance this starting with the metals. So we have 2 sodiums here. I have only 1 sodium here. Let me move this over a little bit to give myself some room. Here, let me rewrite this. So I have H2CO3 aqueous plus, and then this is going to be NaNO3 aqueous. Okay, so I need 2 there to balance the 2 sodiums here. And then I have NO3. I have 1 NO3 here. So I'm going to balance the 1 NO3. That's 2 NO3s there. So I'm going to need a 2 there. Okay, so I have 2 NO3s, 2 NO3s. I have 2 H's here, and that gives me the 2 H's there. That balances the 2 H's there. And then now I have the 1 carbonate there, the 1 carbonate there. So this is balanced. So now I have my balanced equation. So now I can do the stoichiometry. So now I'm looking at my problem. They want to know the milliliters. I need the volume in milliliters of the 6 molar HNO3 solution. That's where I need to go. But what are they giving me? They're giving me the molarity of the HNO3. So that's a conversion factor that I will use. And then they're giving me the molarity of the sodium carbonate. That's a molarity. That's a conversion factor that I will use. So the only thing that's not a conversion factor is the 75 milliliters of the sodium carbonate. So I'm going to start with that. I'm going to convert 75 milliliters of the sodium carbonate to milliliters of the HNO3. So start with the 75 milliliters. So I have 75.0 milliliters of this substance, and that substance is the Na2CO3. Okay. Then I'm going to put that over 1. And so now I need to convert this to moles. That's the goal. The first thing you need to get to is moles. I need to get to moles of Na2CO3, sodium carbonate. So where am I on my roadmap here? I'm at units of volume, milliliters. So I need to convert this to liters, and then I'm going to use the molarity as a conversion factor to get to moles. So this is 2 steps. So I know 1,000 milliliters, so 10 to the 3rd milliliters of the Na2CO3 solution is on the bottom, and that's equal to 1 liter of the Na2CO3 solution. So the milliliters of the sodium carbonate cancel out. Now I have liters. Now I can use the molarity of the sodium carbonate to convert to moles. So the sodium carbonate here, or the molarity of the sodium carbonate here, tells me that this is 0.250 moles of the sodium carbonate per liter of the solution. So since I have liters on the top, I'm going to put liters of the solution. So 1 liter of the sodium carbonate, that should be a 2 sodium carbonate solution, and I have 0.250 moles of the sodium carbonate solution. I'm going to write these numbers better. Okay, so liters of the sodium carbonate cancel out. Now I have moles of the sodium carbonate, and so I keep going. Now I'm at moles of the sodium carbonate. I need to get the moles of the nitric acid, HNO3. So that's where the mole ratio is going to come in. So I have 2 moles of the HNO3 to 1 mole of the sodium carbonate. So it's a 2-to-1 ratio. So here I have moles of Na2CO3 on the top. So I want moles of this on the bottom. So it's going to be 1 mole. So 1 mole of the Na2CO3 on top, and then the 2 moles of HNO3 on the top here. So this on the bottom, this on the top. Okay, so then the moles of the sodium carbonate cancel out. And now I have moles of my nitric acid. So now I've gone from moles of substance 1 to moles of substance 2 using the mole ratio. Now I need to get to whatever unit I need to get to. In this case, milliliters. So now I need to get to milliliters of this HNO3 solution. So I'm going to keep going. So I'm going to continue down here. So now I need to use the molarity to convert to liters. They give me the molarity 6.0 molar. So that means it's 6.00 moles per liter. So here I have moles on top. So it's going to be 6.00 moles of HNO3 on the bottom and 1 liter of the HNO3 solution on top. So the moles of HNO3 cancel out. Now I have liters, and so I'm going to keep going. I want milliliters, so now I'm going to use the same relationship. 1 liter is equal to 1,000 milliliters. So this time 1 liter goes on the bottom, 1 liter of HNO3 solution, and 10 to the third, or 1,000 milliliters of HNO3 solution on top. So liters cancels out. I am all done. So now all I need to do is multiply across the top, divide by everything on the bottom, and I get my answer. And let me see what I calculated. And it is 6.25 milliliters of this concentrated acid HNO3. So 6 molar of this acid. So it'll take 6.25 milliliters of 6 molar nitric acid to neutralize 75 milliliters of this molarity of my carbonate. Okay, so now with regard to sig figs, for those of you interested in sig figs here, remember that the rule is when you're multiplying and dividing, that the number of sig figs in your answer should equal or be the same as the least number of sig figs in your measurements. So here we're ignoring the exact measurements or exact relationships. So the metric to metric volume is exact here as well. That's exact. We'll ignore those. The mole ratio is exact, so we'll ignore those. So the ones we're going to focus on then is the molarity. That's a measurement. That's 3 sig figs. We have here the molarity. That's going to be 3 sig figs there. And we have 3 sig figs in the volume we were given. So 3 is the number. So therefore, our answer should be in 3 sig figs. So there you go. And that, ladies and gentlemen, is it for this video. I hope you enjoyed the video. I hope this problem makes sense and helped you out. If this video helped you out in any way, then please, by all means, like the video, share the video with your friends, hit that like button over there somewhere. And then also make sure you subscribe to my channel, hit that notification bell. When you do, make sure you click all so you'll be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Also, if you have a particular problem you want me to go over with you, or a particular question you need answered, or if you have a topic you want me to cover, I would love to do that for you. Thanks for joining me and have a great day.